Hello everyone, this is caller from 19. Today's day 101 in my challenge day. And today I'm going to learn about the ray sphere intersection in the ray tracing course. And if I have time, I'm going to look around the surface numerator. Okay, let's start.
Because both sides, and the rest is going. Okay, so why don't we start? After being immersed into the beauty of Fresnel's law, Fresnel's equation, and Snell's law, we are going to continue with kind of putting together a new ray tracing problem. And we know all about air-glass interactions and things like that, but we, for instance, don't know what a representation of a ray of light could be. So let's go with this. So a ray is basically starting somewhere and it is going somewhere. That's basically it. This is what I have written here mathematically. So this is a parametric equation. We'll talk about this in a second. So O is the origin. This is where we start from. D is a direction vector. This is where the ray is going, and T is the distance that it had gone. That's basically it. So if T is a large number, then the ray had traveled a lot, and if T is 1, then that's unit distance. Now, we are always going to talk about vectors of unit length if we are talking about direction vector. And most vectors are normed in global illumination anyway, but I would like to state this because now this T is meaningful. If D is of unit length, then T is a scalar, it's a number, it tells you the distance that is traveled. And this notation is a bit weird for many people because this R depends on T. And if you come from the regular math courses, most of what you encounter is implicit equations. So this could be an equation of a surface, f of x and y equals 0. For instance, this is an example. This would be the implicit equation of a sphere. And this is an equation, so basically you can say that whatever x and y does satisfy this equation is going to be the point of this sphere. And this is going to be this collection of points that gives you a sphere. And parametric equations don't look like that. So with these parametric equations, you can see that the x-coordinate I can dig out from a function that depends on t. The y-coordinate I can dig out from a different, perhaps a different function, but it also depends on t. And I can write up this whole thing as a vector form, so I'm not talking about x, y, but probably vectors. So let's see an example. The equation of array is such an example that you have seen above, but we're going to play a bit more with this. And the first question is, why are we doing this? Why parametric equations instead of implicit functions? Well, you will see soon enough when we encounter a problem, and this is going to be easy to solve with parametric equations. So this is a secret. And now, let's try to compute the intersection of a ray and a sphere. So I cast a ray, and I would like to know which is the first object that I hit in the scene. And if I have a scene of spheres, then this is the kind of calculation that I need to do. So the expectation first of a ray and the sphere. So I cast a ray and I would like to know which is the first object that I hit in the scene. And if I have a scene of spheres, then this is the kind of calculation that I need to do. So the expectations are the following. I have a sphere and the ray, and it is possible that the ray hits the sphere in two different points. Well, what else is possible? If two hit points are possible, then one hit point is also possible. This is essentially the tangent of a sphere. It is just hitting it at the very side, while this is rare. site, but this still exists. And obviously, it is possible that the ray does not hit the sphere at all. So we have, again, listed our expectations before doing any kind of calculation, and you will see that this will make things much more beautiful. So the solution for this whole problem should be some kind of mathematical something that can give me two solutions, one solution, or maybe no solutions. If I do the intersection routine and I get whatever else, then this should be incorrect. So this is what I expect to see. There's possibility of 2, 1, or 0 solutions. Well, this is the equation of a sphere. The P's are going to be the points on the surface of the sphere, and the C is the center of the sphere, and R is obviously the radius. This is the equation of the ray. We have to mix these two together in some way in order to get an intersection. What I'm going to do is I'm going to substitute this R of t in the place of P. So what it will give me is O plus Td minus C times O plus Td minus C equals R squared. So this is a big multiplication between the two parentheses. And if I do this actual multiplication, then I will see that there's going to be a term which gives me the Td times Td. So there's going to be something like T squared D squared. here. And there's going to be another term where the O minus C is multiplied with the TD on the other side. And this happens. Happens twice because both sides. and the rest is going to be a scalar term because O minus C, I'm going to multiply with O minus C, so this is going to be a scalar. I don't see T in there. And this is already quite interesting because if we smell this equation, what does this equation? equations smell like? Raise your hand if you have some idea on what this smells like. Yes, that's going to be correct. Yes.
Yeah, it's a polynomial equation of what is it called, degree 2?
Exactly. So this is, but I have to smell it first. So yes, indeed, that's a quadratic equation. So I have t squared, t and the scalar term equals 0. What are the coefficients? Well, simple. The t is going to be t squared. What about the b? Because the t2 that satisfies this equation. And now the someone help me out. I missed some courses at kindergarten, so I don't know anything about this. Interesting part during this, and it's so true. Is it possible when the term under the square root is going to be a number, some real number, and therefore this is going to be t1 is minus b plus this number, t2 is a minus b minus this number, and therefore this is going to be two different solutions. Maybe I shouldn't walk so much during the course. Can you hear this? So this is quite beautiful because we listed our expectations and it indeed needs to look like something that can give me 2, 1, or 0 solutions. And if I do the math, this is exactly what happens. So this is the beauty of the whole thing. And let's imagine that I've solved this equation and I got the result that t1 is 2 and t2 is minus 2. And now, what if I told you that these t's mean distances? So I'm solving the parametric equations in a way that this t means a distance. So it means that the first intersection is 2 times the unit distance, therefore 2 in the front. There could be a solution, which is a classical case for a quadratic equation, where I get a second solution that is minus something. What does it mean? Yes?
I think we can dismiss that because it's behind our eyes, so we don't really care about that, do we?
Precisely. So it is possible that the ray starts in the middle of the sphere, and then this is indeed a perfectly normal thing to happen, that there's one intersection in front of us, and there's one intersection to our backs. And obviously we don't care about it too much. And if we find a solution like this, we discard it, indeed. So we're studying computer science, and we are not studying politics, because if we would be studying politics, we would be interested in what happens behind our backs. But this is computer science, so we can discard all this information. Okay, let's quickly start.
Okay, so I raise peer intersection from today's course. So first we need to abstract the ray as its origin and is the ray's direction, also the distance coefficient of the direction. So because we are going to use the t as the distance coefficient of the ray direction, so we need to set the magnitude of the direction vector should be 0, as a 1. That is that it should be normalized whenever we calculate some intersection between the ray and some geometries. So if we convert this ray into the equation form, we can represent it ray as RT is equal to its origin plus t dot product with the d as a direction. As I already mentioned, the t represents the distance of the ray. When we represent the geometry in the computer graphics, there are some of the ways to do that. The one method is to represent it as an implicit function, or in the rasterization pipeline, we can use a triangle mesh as we already know it. So in the latter case, we need to use the triangle and the ray intersection method for that. Or if we use the for the implicit uh, equation for the geometry, then we need to set some various the equation relationship between the ray and the certain geometry. But in this lecture, we just caring about the ray sphere intersection. So we can represent a circle in the two-dimensional space with the center of the circle and the radius r can be will be shown as with this equation. So x and y is a certain point on the circle, and a b as a center of the circle. So if we subtract x and x, uh, if we subtract x by a and y by b, and the square of that and minus r square should be equal to 0 to satisfy the circle shape. In the meanwhile, we can use the parametric equation can be to replace the which of variables individually, like x is equal to xt and y is equal to yt. There can be a three intersection event with the ray uh, event between the ray and the sphere. The first one is a hitting point can be a 2, or the hit point exactly can be a 1, which is the tangented case. And the last one is the ray when the ray missed. It means that there is no hit at all. So the last thing is to find the roots for the intersection equation with the given informations that what we know that is the point of the what we know that is the form of equation of the sphere and the ray equation, and we know the origin of ray, and we know the direction of the ray. Also, we know the center of the sphere, and we know the radius of the sphere. So with this given information, we can we can substitute some variables with these informations. So we can represent it, we can show that as this equation. So this is the ray part, and this is the center of the sphere, and dot product of two of them, and it should be equal to the radius, a square of the radius. Because we know the origin and the direction of the ray, what we just want to know that is what is the value of the t, so that we can know what is the intersection point on the sphere, so that we can reordering this equation in terms of the t by substituting O minus C as a plus TD and dot product of itself. And we can proceed the equation algebraically. Then we can reorder the equation in terms of t, because we want to solve the equation for the t. And if you're familiar to the middle school math in the Korean education course, we know that we have a formula to solve the quadratic equation with this famous formula. When the equation form is ax squared plus bx plus c is equal to 0, and we say that the expression, let me just write, the expression resides in the square root is called as a determinant of this formula. So if the determinant is lower than 0, there is no, it means that it's a minus is under 0. It means the imaginary number, so we don't have any root for that. So this is exactly the missed case. And when the determinant is exactly equal to 0, that means that the square root term will be discarded. We only have the single root for the case. So it means that it's exactly the same with this one hitting point in the intersection event. For the last case, where is the determinant is bigger than 0, it means that there will be two roots against the given equation. So especially when there are more than one solution, we can ignore the bigger roots because it is occluded by the front face of the mesh, which is we can see because the back face of the mesh. So for the intuition, let's think about this sphere. So if we shoot the ray here, and when there's more than one root, the ray will have a root for the sphere with this point and a refracted and this backface root. But what we can see only that is the front face of this sphere. So we have two roots. Which one is the one is smaller than the other, and what we only need to do that what we only need to get is just the smaller root, because the bigger root, that is the root that we can't see. So this was the key review for the ray sphere intersection in the ray tracing. Hopefully this can be helpful your understanding. And that's all for today's recording, and thanks for watching. See you next video. Bye bye.